Predicting the pH at the equivalence point of an acid-base titration, part 2. So today we're going to wrap it up. What is the pH at the equivalence point of these acid-base titrations? And like we said before, a titration is a very inexpensive way to get an exact amount of an analyte in a system. So whether it's in the environment or in the wine industry or the pharmaceutical industry, it's a very cheap way to get really good answers in chemical systems. So predicting the pH at the equivalence point of an acid-base titration, part 2. What is the Ka or Kb chemical reaction that controls the pH at the equivalence point for each acid-base titration? So we're just going to practice a few of these. We are titrating hydrocyanic acid with NaOH. And what helps me is if you titrate with a base, you get a base. Titrate with an acid, you get an acid. We're titrating with a base, so we're going to get a base. So what are we going to get? We're going to get cyanide, right? The conjugate base of hydrocyanic acid. But they want to know what is the Ka or Kb chemical reaction. So we have to write a Kb reaction then. Cyanide plus water forms hydrogen cyanide plus hydroxide. The Kb reaction, forming hydroxide. The titration of hydrofluoric acid with sodium hydroxide. Again, titrate with a base, get a base. So fluoride plus water forms hydrofluoric acid and hydroxide. Another Kb reaction. Titration of methylamine with hydrochloric acid. So we're titrating with an acid, we're going to get an acid. So we have to write a Ka reaction. Now what's methylamine? If you don't have it memorized, just find the table. You're given the tables all, right? And where do you look? Well, you're titrating with an acid, so that means this must be a base. So look in the base ionization table. Here's methylamine. So to make its conjugate acid, just throw an H out front. Okay. Ka reaction for the conjugate acid of methylamine. 12 grams of acetic acid was dissolved in 50 mils of water and titrated with 2.8 molar NaOH. At the equivalence point, what conjugate acid or base is present that controls the pH, and what is its concentration? So the same thing we did last class period. So what is the conjugate that we're looking for? Titrate with a base, get a base. You're starting with acetic acid. You're going to get its conjugate, right? Acetate. That's going to be the moles of acetate all over the total liters of solution, total volume. Right, the initial plus the equivalence point. We could actually write that. It might look better. That'll be the initial plus the equivalence point in liters. Now our moles of acetate isn't going to be found in the usual way because did you see what they gave us? 12 grams of acetic acid. So we just convert those grams to moles of acetic acid, and it's the same. We have the moles of acetic acid is going to be the same as the moles of acetate. So 12 grams of acetic acid, and just convert that into moles. How many grams are in a mole of acetic acid? Well, we've got, 4 hydrogens total. That's 4.04 plus 2 times 12.01 plus 2 times 16, about 60.06 grams. All right, for every 1 mole of acetic acid. And you don't need to write this next step, but for every 1 mole of acetic acid, I have 1 mole of acetate. I just didn't want to skip any steps. Right? It's 1 to 1. That's So about 0.2 moles. My initial volume is dissolved in 50 mils of water. So that is going to be 0.05 liters. Now I have to find that equivalence point, right? So to find that equivalence point, I'm going to start with the 12 grams of acetic acid. I'm going to convert it to liters of NaOH. That's what I need, and that will be my equivalence point. So let's start with this 12 grams of acetic acid. It's all going to get reacted up. Right? And I have 60 grams in a mole, 60.06 grams in a mole of this acetic acid. And they're always reacting 1-to-1 with our base, all monoprotic acids. Now I'm finally in moles of NaOH, right? So I can convert to liters of NaOH using the concentration. 2.8 moles of NaOH in a liter of NaOH solution. 12 divided by 60.06 divided by 2.8, 0.071 liters. So I can finally get my final acetate concentration here. .2 moles divided by 0.05 liters plus 0.071 liters. 0.2 divided by parentheses 0.05 plus 0.071, 1.65 molar acetate. Okay. Find the pH at the equivalence point. Okay, now we're going to do the full circle here. The steps in finding the pH at the equivalence point of an acid-base titration. First step, determine the concentration of the conjugate acid or base formed at the equivalence point. Got it. We're done with that. We know that it's 1.65. It's 1.65 molar acetate. Step 2, write the appropriate Ka or Kb chemical equation and use ice to solve for hydrogen ion or hydroxide, and then get our pH. Okay? Well, it's acetate. We have to write a Kb reaction. Oh, I forgot to add my water. All right? Kb reaction, conjugate base plus water, forms hydroxide and the conjugate acid. Okay, I have to do ice of that. Water never shows up in our Kb expression. Acetate, initially I had 1.65 molar. No hydroxide or acetic acid present initially because, right, all that acetic acid was reacted up. I stopped at the equivalence point. Minus X for reactants, positive X for products. 1.65 minus X, X, and X. So Kb, which is equal to Kw over Ka, I'm going to have to calculate that, aren't I? 1 times 10 to the negative 14 divided by Ka for acetic acid. There it is. Ka for acetic acid is 1.7 times 10 to the negative 5. 1.7 times 10 to the negative 5. 1 times 10 to the negative 14 divided by 1.7 times 10 to the negative 5. It's about 5.88 times 10 to the negative 10. We like that 10 to the negative 10, right? Do you remember why? Products over reactants. That's going to be x squared divided by 1.65 minus x. Now, do you remember why we like that 10 to the negative 10? 10 to the negative 10. So we can drop. That 10 to the negative 10 means that we have very small amount of product, right? Because equilibrium constants are products over reactants. If it's 10 to the negative 10, it's a very small number. So x has to be extremely small. Take 1.65 minus a very small number, you get 1.65. So we don't have to do that full quadratic problem. So 5.88 times 10 to the negative 10 times 1.65, take the square root, about 3.11 times 10 to the negative 5. See? So take 1.65 minus 3 times 10 to the negative 5, you get 1.65 again. Okay, so if x is 3.11 times 10 to the negative 5, x is what? X is hydroxide. So that equals my hydroxide concentration. So let's find POH. All right, take the log of it. 4.51. So that means pH has to be, subtract from 14, about 9.5. So when I titrate 12 grams of acetic acid with sodium hydroxide, and I stop at the equivalence point, the pH will be 9.5. What is the pH at the equivalence point when 35 mils of 0.28 molar methylamine is titrated with hydrochloric acid? So determine which conjugate acid or base is present at the equivalence point, determine its initial concentration, write the corresponding Ka or Kb reaction, do ice, get the pH. Try it. So we're titrating with an acid, so we're going to get an acid, right? So we're going to have to write a Ka reaction, but let's determine what this initial concentration is first. We have methylamine. Do you remember what that was? Go back up into our table, right? CH3NH2 is methylamine. And it had a Kb. Well, let's go ahead and write that right away. It had a Kb of 4.4 times 10 to the negative 4. So what we're after then is its conjugate acid, because they're titrating with an acid. All right, what is its? We need the moles. All over the initial and the equivalence point. Okay, so our initial moles is kind of the easy part. Our initial moles is going to be 0.035 liters times 0.28 moles in a liter. Our initial is 0.035 liters. What's that equivalence point? Right? Start with the 35 mils of the methylamine, convert that, well, really you're converting all of this to liters of HCl. 0.035 liters. And I have in a liter, I have 0.28 moles of methylamine. And for every 1 mole of methylamine, I have 1 mole of HCl and 0.21 moles of HCl in every liter of that HCl solution. 0.035 times 0.28 divided by 0.21, 0.047. Okay. .035 liters times 0.28 moles in a liter divided by my initial volume plus my equivalence point. .035 times 0.28 divided by parentheses 0.035 plus 0.047 close parentheses equals 0.1195. Okay, so that's my initial concentration of my conjugate acid. So now I have to do ice, right? Goes to the hydrogen ion and the conjugate base. Initially, I have 0.1195, nothing, minus x, 0.1195 minus x, and x. And we know that the Kb is 4.4 times 10 negative 4. So my Ka is Kw over Kb, 1 times 10 to the negative 14 divided by 4.4 times 10 to the negative 4, right? Yeah, 4.4 times 10 to the negative 4. 1 times 10 to the negative 14 divided by 4.4 times 10 to the negative 4, about 2.27 times 10 to the negative 11. And that has to be equal to products over reactants, x squared divided by 0.1195 minus x. I like that negative 11, so it's approximately x squared all over 0.1195. So what do you get for x? 2.27 times 10 to the negative 11 times 0.1195 equals square root about 1.65 times 10 to the negative 6, and x in this case is my hydrogen ion concentration. So I'll just take the log and we'll have pH 5.78. So 5.78. What is the pH at the equivalence point when 45 mils of 0.28 molar benzoic acid is titrated with 0.31 molar NaOH? So let's find out that initial concentration. And you're titrating with a base, so you're going to get a base. What is benzoic acid? Not sure of the formula? Find it. Here it is. That's going to be the moles over the liters. So I would have 0.045 liters times 0.28 moles per liter. And I have to divide it by the initial volume plus the equivalence point. Okay, let's find out what that equivalence point is going to be. Start with the known, and we'll convert that to liters of NaOH. 0.045 liters. And in a liter, I've got 0.28 moles of this benzoic acid. And then the reacts 1 to 1. And every 0.31 moles of NaOH, I have a liter of solution. So 0.045 times 0.28 divided by 0.31, about 0.0406 liters. So about 0.147 molar. Okay, there's my starting point, so I can make my ice table. And since I titrated with a base, I'm going to get a base. I have to write a Kb reaction. Write a Kb reaction. Plus water, conjugate base plus water, forms hydroxide, Kb reaction, plus the conjugate acid. Ice. The initial was 0.147. Water never shows up. Nothing there initially for the products. Minus X for reactants, positive X products. 0.147 minus X, X, and X. So my Kb is Kw over Ka. 1 times 10 to the negative 14. And what's the Ka for benzoic acid? The Ka is 6.3 times 10 to the negative 5. 6.3 times 10 to the negative 5. .59 about times 10 to the negative 10 will be my Kb. Okay, well, that's my Kb. 1.59 times 10 to the negative 10 has to equal products over reactants. X squared divided by 0.147 minus X. I like that 10 to the negative 10. So we can say 1.59 times 10 to the negative 10 is the same as X squared over over 0.147. So what do I get for X? Times 0.147 equals square root about 4.83 times 10 to the negative 6. That's my X. Go back to your ice table to see what X is. X is hydroxide. So that means we can get POH. Take the log, 5.32. So that means we can get pH then. Finally, add it to 14, or subtract from 14. 8.68. is my pH. So to get the pH at the equivalence point for these titrations, first thing you do is determine what that conjugate is, what formed at the equivalence point, and get its initial concentration. And it's always the moles that you started with of that weak acid or weak base divided by the total volume. That's going to be the initial plus the equivalence point. And how do you get that equivalence point? Always just start with what you're given and convert it to the volume of titrant in liters. Get that initial concentration, write the corresponding Ka or Kb reaction, and do ice. Then you can get your hydroxide or hydrogen ion concentration and pH.